Hi, my name is Nabas. I'm the project manager for the OpenBCI project. And today I'm going to present this project together with two of my project members, Eddie and Saji. So this presentation is going to be structured like this. We're going to go through some background, give you some motivation for the project, the project goal, and our approach to how to achieve our goal. And then we're going to present some results and tell you what's left to do in the future. But BCI, what's BCI? BCI stands for Brain-Computer Interface, and it's a relatively new research field that started in the 1970s. BCI systems usually aim at helping the brain communicate with external devices without any limbs, basically. And research in BCI is usually aimed at mapping, assisting, augmenting, or repairing human cognitive or sensory functions. Throughout this project, we've been using products from OpenBCI. OpenBCI develops open source software as well as selling some equipment to measure EEG data with. The equipment we've mainly been using throughout the project was the site on board together with the headset that you see over there to collect our data. So this project started as most other BCI projects to help physically impaired people and the disabled, like people who are suffering from Parkinson's, stroke patients, and other such diseases. But of course, BCI can also be applied in many other different areas like gaming and maybe military stuff, and yeah. So the goal for our project was to create a real-time application that would control the mechanical hand. And we decided to do that in two parts. One, offline analysis, and then analyzing everything online. Or using what we've learned from the offline analysis and then implementing it in real time. So our approach was to collect data in a safe environment, controlled environment, and then pre-process that data to remove all kinds of noise and corruption from the data. And once we had done that, we would extract and calculate features to get more relevant data that the classifier can then train and interpret. And once we had done that a few times offline, we implemented the best methods in our online application.
So I'm going to be talking about briefly about some of the approaches that we use to tackle the different parts. So for the data acquisition, first we set up a room which could avoid disturbances. So we had a dark room. It was isolated, and the subject sat alone in the room to avoid visual and audio disturbances. We have a fixed amount of iterations, and so to perform the experiment, we asked the subject to not take any substances that could affect the brain activity. We asked the subject to sit in front of the computer with the headgear on, and we had three instructions: a plus sign, minus sign, and a relax sign. The plus sign meant that the subject should open and close the hand. The minus sign meant that the subject should remain not doing anything, and the relax was just to get some time in between the two states. And the instructions were really simple, just to avoid any kind of disturbances for the brain. So for pre-processing, we chose to use bandpass to let the frequencies in between 0.3 to 38, which were the relevant ones for us. And yeah, we use the Chebyshev method, Butterworth, Equiripple, and looking to the results, we observed that the Chebyshev gave the best result out of the three, so that's why we decided to go further to the online implementation with the Chebyshev. Here. In the left picture, we can see the raw data for the channel 3, which was placed around here, which is a really important part for our purposes, which is motor imagery. And on the right-hand side, you can see the filter data with the Chebyshev. So for feature extraction, we use two approaches, like wavelet transform and fast Fourier transform. And here's what the fast Fourier transform gave the best result out of the two, and that's why we decided to further implement this in the online application, because we could see with the fast Fourier transform we could see the data in the frequency domain, and we could clearly see the features we needed, which was alpha and beta. We could clearly see the frequencies. I'm going to show you. So here in this table, we can see the frequency bands, and the ones we needed for our purpose was alpha and beta, more in between 8 hertz to 20 hertz. And we used, so we had two features per channel, which was the mean of alpha and the mean of beta. And here we can see the fast Fourier transform performed on a window. So we separate into windows, each window being 256 samples, which was 1 second. And we can see in the lower frequencies there's a lot of activity, but we'll just focus in the frequencies between 8 and 20, which was the most relevant for us.
For the classification part, we implemented two algorithms. One is a support vector machine, and the other one is linear discriminant analysis. The accuracy of these algorithms were observed, and the plots and the confusion matrix will be shown in the future slides. First, coming to the SVM, it is an algorithm that is used for nonlinear data by using different kernel functions, even though the SVM is linear in nature. What SVM does is that it detects pattern within the data, and then it classifies the given data into 1, 2, or more classes. And the main goal of the SVM is that whenever a new data comes in, it should choose to which class does this new data belong to. Now looking at the plot, we see that the algorithm that we designed has a greater affinity to classify the data for class 2, which in our case is the idle case. And looking at the confusion matrix, we see that for every 256 samples, the SVM, it predicts 71 right and 57 wrong for class 1, and 49 wrong and 79 right for class 2. The accuracy that we obtained in SVM was around 59%, and this was done by using the classification learner app in MATLAB. Next, coming on to LDA, this algorithm is used to find linear combination of features that can better separate the two classes. And one of the advantages of LDA is that it provides maximum separation between the classes so that the data is easily separable. And the plot over here again shows that for the data that we feed into the algorithm, it is more lenient towards classifying for class 2. And the accuracy that we obtained over here was 53%, and this was developed from scratch with 75% of the data to be given for testing and 25% for training. Lastly, coming on to the results, the offline classifier that we designed is used in the online classification so that whenever we feed in the new input data, it classifies to which class does each of this belong to. And while doing this, we focused on one main problem, that is, the classifier was always using the new data to classify for the idle state, and there were several reasons for this. When we look at the plot below, we see that the global mean for both the motion state and the idle state is vastly different or is more similar to each other. So this presents a problem that whenever a new data comes in, the classifier finds it difficult to which class does the data needs to belong to. And looking at this plot, we look at the data that we collected from two different subjects and the features that we extracted from there. The global mean for both the subjects, they vary vastly. And for the subject 1, due to different outliers, several outliers that we have in the data, it pushes the mean a little bit upwards. And for subject 2, we notice that the global mean is much more different for the one from subject 1. Next, we look at the online features that we obtain from channel 3, which in our case is the alpha band. And over here we see that the global mean is very low. So this means that whenever the new data comes in, it always classifies to the closer mean for the idle state. And lastly, this is another reason where if we use to collect the data from the same subjects but in different sessions, one may be in the morning and the other may be in the afternoon, the global mean of the features are also differ vastly in this. This is due to many biological factors and also other reasons such as the state of the mind, stress, or the injection of caffeine. The proof of concept that we had shown in the previous slides, we are able to achieve that by using a dummy data through which we designed the classifier, and we sent in the data into the lab view. And for both the states, that is for the hand closing and for the hand opening, it works. But in order to design a more general classifier that works on different data sets, future work needs to be done on that.
So here's a list of things that we think should be done in the future. We think that mostly the next group should focus on feature extraction and using EMG sensors in combination with our headset to improve the accuracy of the classifiers. And also some improvements need to be done on the online application. So, thank you. If you have any quick questions, we can take them now. Or if you want to talk to us more, we're over there, and we'll answer all your questions. Thanks.